Welcome to this webinar series. We call that W2S webinar series on spintronics. Today we will have the lecture by Professor Yuya Sakuraba from National Institute of Material Science, very well known as NIMS, Tsukuba in Japan. First of all, I like to really thank joining this webinar from a very late evening for him. It is now 10 p.m. in Japan. I really appreciate that he is joining and giving us this kind lecture. So you may know him, but as a matter of formality, I would introduce him. So Professor Sakuraba got his BS from Tohoku University in 2001. Then he got his MS in 2003 from Department of Atomic Physics, Graduate School of Engineering, Tohoku University. Between 2004 and 2006, he pursued his PhD degree and he obtained it from the Graduate School of Engineering in Tohoku University in Sendai in Japan, where actually he worked for some time in 2005 and 2006. He was a fellow from Japan Society for Promotion Science, JSPS. And since 2007 till 2012, he was an assistant professor in magnetic materials laboratory of Professor Koki Takanashi at Institute for Material Research in Tohoku University in Japan. And then he moved to NIMS in Tsukuba in 2013 as a senior researcher in the magnetic materials unit in the group of Professor Huno at NIMS. And since 2018, he is now working there as a group leader for the magnetic materials group at NIMS. His research interests are spintronics phenomena and materials, especially functional Heuster alloys, thermoelectric effects, and their applications using magnetic materials. He has obtained numerous awards. In 2007, he got the 29th JSAP Award, JJP Paper Award. 2008, he got the award for the Funai Foundation of Information Technology. In 2008, he got the Distinguished Paper Award by the Magnetic Society of Japan. 2010, he got the 50th Harada Young Scientist Award. 2012, he got the Young Researcher Award by Asian Union of Magnetic Science Societies, that is known as AUMS. 2013, he got Tokin Foundation for Advancement of Science and Technology, 23rd Research Encouragement Award, the highest award. 2014, he got the 27th Young Researcher Award of the Hiroshi Ando Foundation. 2015, he got Outstanding Research Award of Magnetic Society of Japan. And 2018, he got the Young Scientist Prize of Minister of Education, Culture, Sports and Science. And in 2018, he got the 28th Tsukuba Encouragement Prize. So really noticeable, numerous recognitions. So with this short introduction, I welcome again Professor Sakuraba and for his lecture, and for the participants who are kindly joining this webinar, I request them to mute their microphone and switch off their videos throughout the webinar. And if you have a question, you can kindly write that in the chat window. And at the end of the lecture, we will try to take all the questions one by one. Okay, with this note, so I request Professor Sakuraba to continue his webinar. Thank you very much.
Okay, thank you for very kind introduction, Vedanta-san. So my name is Yuya Sakuraba. I'm from the National Institute for Material Science, Japan. Okay, first of all, I'd like to thank the Professor Vedanta and Professor Singh for giving me very nice opportunity to talk about our study. So as a researcher in NIMS, I'm now working on the several research topics The main topics is development of spintronics device using the half-metallic Heusler alloys. But today I'd like to show you the result in my kind of second topics. So the novel thermoelectric application using the anomalous Nernst effect. So the title of my talk today is Anomalous Nernst effect for novel thermoelectric application and development of magnetic material and prototype devices. So here you can see the collaborator of this project. Okay, here you can see the outline of my talk today. So first, I'd like to introduce the background of our research. So I want to explain the fundamentals of anomalous Nernst effect. And I want to explain what is the advantage of thermoelectric application using the anomalous Nernst effect is. And I want to introduce the two promising applications using the anomalous Nernst effect. The first one is the energy harvesting technology. The second one is the heat flux sensor. As I will mention later, one of the serious requirement to realize this kind of application is to get a large thermal power of anomalous Nernst effect. So today I want to explain how we can get the larger thermal power of anomalous Nernst effect. After that, I want to show you the experimental result of anomalous Nernst effect in the two different kind of material, the cobalt-based Heusler alloy thin films and the iron-based binary alloy thin film. And actually, we already fabricate the prototype of heat flux sensor using the anomalous Nernst effect. So I'd like to show you the result of demonstration of heat flux sensing using this prototype device. Okay. Okay, so first I'd like to mention the background of our study. As you know, the Seebeck effect is the most conventional thermoelectric phenomena in conductive material. When we give the temperature gradient, so we can obtain the electric field to the same direction of temperature gradient. And the direction of Seebeck electric field depend on the sign of the Seebeck quotient. And as you know, that there's a long history and huge number of studies for Seebeck effect, especially for the thermoelectric power generation. But recently, researchers in spintronics and magnetic society interested in this special thermoelectric phenomenon in the magnetic material, which is called the anomalous Nernst effect. Anomalous Nernst effect can give the electric field to the perpendicular direction to both given temperature gradient and also the magnetization direction. So the electric field of the anomalous Nernst effect can be expressed by this kind of equation. So here you may notice that the electric field direction of anomalous Nernst effect can be controlled by the direction of the magnetization. And the most important advantage of anomalous Nernst effect is that we can get the electric field to perpendicular direction to the given temperature gradient. So as you can find, so Seebeck effect is kind of one-dimensional effect, but the anomalous Nernst effect is three-dimensional effect. So this three-dimensionality gives us the more freedom to design the novel thermoelectric applications. That is the most important point of anomalous Nernst effect for this application. So let me explain the detail of advantage of anomalous Nernst effect for thermoelectric applications. So as you may know, the Zeebeck-based thermoelectric module, such as a electric power generator or a heat flux sensor, usually have this kind of thermopile structure. So as you can see, this kind of complex thermopile structure is required to obtain the high serial voltage in Zeebeck module. So, but because of this complex structure, so Zeebeck module is usually mechanically very fragile, and it is not easy to use the large heat source having the non-flat surface. And as you may know, the ZT, non-field of merit that determine the energy conversion efficiency is limited by the Wiedemann-Franz law, because electric conductivity and thermal conductivity appear the denominator and numerator. So there is a limitation to improve the ZT because of the limitation of Wiedemann-Franz law. However, when we consider to apply the anomalous Nernst effect for the thermoelectric applications, so we don't need to make this kind of complex thermopile structure anymore. We can easily increase the serial voltage by making the laterally connected ferromagnetic wire like this. So because the electric field of anomalous Nernst effect appear along the surface of heat source. So in this figure, the magnetization direction is X direction. So the electric field of anomalous Nernst effect appear to the this direction, Y direction. So we can easily obtain the high serial voltage by making this kind of simple lateral connected structure. So because of this simple structure, it is easy to apply large heat source having the non-flat surface. And when we use this kind of three-dimensional shape heat source, such as this kind of tube shape heat source, we don't need to make the thermopile structure anymore. We just need to roll one ferromagnetic wire in spiral. So in this structure, the electric field and anomalous Nernst effect appear to the tangential direction. Therefore, we can easily obtain the high serial output voltage depending on the total length of ferromagnetic wire. And when we see the expression of ZT, we can notice that the sigma and kappa appear to the perpendicular direction. So if the magnetic material have the anisotropic material property, we can control the DT beyond the limitation of Wiedemann-Franz law. That is another important advantage. However, in reality, it is not so easy to realize the practical application using the anomalous Nernst effect because of the too small thermal power of anomalous Nernst effect. In the typical ferromagnet of iron, cobalt, nickel, observed anomalous Nernst thermal power is usually less than 0.3 microvolt per Kelvin, which is 2 or 3 orders smaller than the Zeebeck question. So for realizing the practical application, so large thermal power of anomalous Nernst effect is necessary. So, but anyway, in my previous studies that I performed with Professor Takanashi almost 10 years ago, I made a prototype of thermopile structure using the anomalous Nernst effect. So in this study, because the iron platinum and manganese gallium has the opposite sign of anomalous Nernst coefficient, so I made a laterally connected thermopile structure consisting of the iron platinum and manganese gallium wire. In this study, so we successfully demonstrated the enhancement of output voltage, anomalous Nernst voltage, depending on the total number of pair of iron platinum and manganese gallium wires. And another interesting advantage of anomalous Nernst effect is that we can fabricate a thermopile structure using only one magnetic material. So as I mentioned, in the Seebeck module, because the direction of the Seebeck electric field depends on only the sign of Seebeck coefficient. So it is usually necessary to use the P and N-type semiconductor to form the thermoelectric module. However, in the case of anomalous Nernst effect, direction of anomalous Nernst effect electric field can be controlled by the direction of magnetization in ferromagnetic material. So we don't need to use the two magnetic material having the opposite sign of QS. So as a demonstration, previously we fabricated this kind of anomalous Nernst thermopile structure using only iron platinum. But by changing the deposition condition of iron platinum, we make the iron platinum harder and softer. So by measuring the this hard and soft iron platinum separately, as you can see this figure shows the anomalous Nernst voltage as a function of external magnetic field. As you can see, we can clearly see the difference of coercivity in these two iron platinum wire. So if we measure the anomalous Nernst voltage in for this thermopile structure, so when we applied strong external magnetic field, because all of iron platinum magnetization aligned to the same direction, we cannot get the high anomalous Nernst voltage. But with decreasing the external magnetic field, around here, only the soft iron platinum magnetization reverses to the opposite direction. Then the electric field of anomalous Nernst effect can be enhanced. So important point here is after we realize this configuration, by reducing the external magnetic field to 0, we can keep this anti-parallel magnetization configuration without any external magnetic field. Then we can we can realize the thermopile structure using only iron platinum. So this is the one demonstration, but this result showed a very promising advantage of anomalous Nernst effect-based thermopile structure. Okay, from here, I want to mention the possible application using the anomalous Nernst effect. The first one is energy harvesting device, and second one is heat flux sensor. So as you know, the number of the sensors in the world is rapidly increasing, as you can see in this figure for the IoT. But now we mainly rely on this kind of button cells as a power supply for these sensors and wireless communication systems. But these recent sensors and wireless communication system required only microwatt and milliwatt level electricity. So it is possible to obtain this kind of electricity from the energy surrounding in this society. For example, the light, vibration, and heat, radio wave. And in this kind of energy sources, the heat is the most common and abundant energy sources in our life. So the many researchers are working on the Seebeck effect to realize the energy harvesting technology. However, we are interested in the anomalous Nernst effect for realizing the energy harvesting technique. So in order to understand how much thermal power is required to realize the anomalous Nernst effect-based energy harvesting, we performed one simple simulation. So because for energy harvesting, we cannot use the very high temperature heat source So usually heat source must have the temperature around room temperature. Here we consider the heat source having the temperature of 50 degrees C, and the heat bath is air of the temperature 30 degrees C. So in this simulation, we insert the magnetic material of 50 centimeter and 50 centimeter area, and the thickness is 2 millimeter. And in order to calculate the obtainable anomalous Nernst power, electric power, we put this kind of typical thermal conductivity and the resistivity in this magnetic material. So in this situation, actually, we cannot get the 20 degrees C difference in this magnetic material because of the existence of very large interfacial thermal resistance between the magnetic material and air. If we put this kind of typical heat transfer coefficient with air, actually almost all temperature difference appears only at the interface. And if we calculate the obtainable temperature gradient in this magnetic material, we notice that obtainable temperature gradient is very, very small, just 0.1 Kelvin per millimeter. So we have to calculate the obtainable power as a function of the thermal power of anomalous Nernst effect under such a small temperature gradient. So as you can see in this figure, if we want to realize the power over 100 microwatt, which is required for energy harvesting technology, at least we need to realize the anomalous Nernst thermal power over 20 microvolt per Kelvin. Of course, this is kind of one example of calculation based on this specific model. But what we can find from this kind of simulation is at least we need to realize a few tenths of microvolt per Kelvin from anomalous Nernst effect for realizing the energy harvesting technique. Okay, and let me introduce another promising application using the anomalous Nernst effect, which is a heat flux sensor. So actually, we already have the commercially available heat flux sensor using the Seebeck effect. So using Seebeck effect-based heat flux sensor also have this kind of thermopile structure, matrix type thermopile structure. And when the heat current passes through this heat current sensor homogeneously, so of course we can obtain the Seebeck voltage between these two electrodes. And because we know the Seebeck voltage and the thermal conductance in this heat flux sensor, we can evaluate the given temperature gradient, and then we can evaluate the heat flux passing through this heat flux sensor. So this is a mechanism to measure the heat flux using the Seebeck effect. So the very important advantage of heat flux sensor compared to the usual thermometer such as thermocouple is that the heat flux sensor can quickly detect both magnitude and also the direction of heat flux. So this quick detection is very important advantage of heat flux sensor. So for example, if we put the heat flux sensor on every window of vehicles or buildings, it might be possible to do the more efficient thermal management to save the energy. And for example, if we put the heat flux sensor having enough flexibility on the human body, it might be possible to monitor how the human is feeling the temperature, because heat flux has the direct information, the feelings. So in this case, maybe the heat flux sensor tells us how this baby is feeling, hot and warm and cold. And for example, if we put the heat flux sensor on the robot, this robot might be able to feel the temperature of the touched object immediately. So this is these are several examples, but we believe heat flux sensor will be more important application in near future. So, however, this kind of Zeebeck-based heat flux sensor, the utilization of Zeebeck-based heat flux sensor has been very limited because of the several serious problems. As you can see, so the Zeebeck heat flux sensor has very complex matrix structure. Basically, it is very expensive. One sensor costs over $300. And it is because of this complex structure, it is difficult to make large and smaller sensors. And it is not easy to bend this kind of complex structure, so there is a limitation of the flexibility of sensor. And also, we have to use the relatively thick substrate to hold this thermopile structure. So usually heat flux sensor, Zeebeck-based heat flux sensor has a very small thermal conductance. So it is heat flux sensor, but by using this heat flux sensor, original heat flux changed by heat flux sensor. So that is a reason why this Zeebeck-based heat flux sensor has been limitedly used. However, we believe we can overcome this kind of problem by using the anomalous Nernst effect-based heat flux sensor. Because this sensor has very simple structure, it is very easy to make the thermopile structure. So we believe we can reduce the cost for one sensor. And it is not difficult to make smaller and larger sensor using the anomalous Nernst effect. And we can reduce the total thickness of this sensor, so we can obtain the much higher flexibility and low thermal resistance. So we believe the anomalous Nernst-based heat flux sensor is very promising, will be very promising application. However, as I mentioned, so low thermal power ANE is the most important subject to realize this heat flux sensor. So again, here to understand the required thermal power of a Nernst effect to realize the heat flux sensor, we performed a very simple simulation. So here we consider the rectangular shape heat flux sensor of the length of L1 and L2. And we put the magnetic material having the width of W and height of H, and the distance between two magnetic materials is D. So in this situation, the sensitivity of this heat flux sensor can be written by this equation here. SANE is the thermal power of Nernst effect, and the copper is thermal conductivity of magnetic material. So to evaluate the specific value here, we put the 1 centimeter size, and the width and height of magnetic material is the 10 micrometer. So in this condition, we calculated the sensitivity of heat flux sensor as a function of thermal power of anomalous Nernst effect. So because the sensitivity is inversely proportional to the thermal conductivity, we put the 3 different thermal conductivity for this simulation. And when the thermal conductivity is 10 watt per meter Kelvin, as you can see, in order to overcome the sensitivity of current commercially available Zeebeck heat flux sensor, so we have to realize over 10 microvolt per Kelvin. So yeah, so for both the energy harvesting and heat flux sensor, we have to realize the thermal power of Ne over a few tenths microvolt per Kelvin. That is a clear requirement for realizing these kind of thermoelectric application. So here we need to consider how can we get the large thermoelectric power, thermal power from the anomalous Nernst effect. So this linear response equation gives us the tips to explore the material having the large anomalous Nernst effect. As you can see, thermal power of anomalous Nernst effect can be divided into these two components. The first term is a product of resistivity and the off-diagonal part of thermoelectric tensor. And the second term is a product of rho xy, anomalous for resistivity, and the diagonal part of thermoelectric tensor. Okay, so this first term and second term must be large, and the electric field from this first and second term constructively work to obtain the high anomalous Nernst effect. And this second term can be converted into the product of Zerbeck coefficient and anomalous Fall angle. The material, we can say that the magnetic material having the large Zerbeck coefficient and large anomalous Fall angle is expected to show the large anomalous Nernst effect. And this alpha xy off-diagonal part of thermoelectric tensor is very important parameter for anomalous Nernst effect. And the Mott relations give this kind of expression. Alpha xy is proportional to the energy derivative of anomalous Fall conductivity at Fermi level. So the anomalous Fall conductivity is important parameter for both first term and second term. Therefore, it is very important to know the anomalous Fall conductivity in magnetic material to realize higher anomalous Nernst effect. So recently, researchers in magnetic society are often interested in this intrinsic anomalous Fall effect arising from the Berry curvature of magnetic material. So Berry curvature of the magnetic material can be expressed by this equation. Here, the denominator is the energy difference between the occupied and unoccupied electronic band, and the numerator is the eigenvalue of the carrier velocity. And from this equation, we can expect it that the Berry curvature can be enhanced when the two electronic band is crossing around the Fermi level. As you can see in this example calculation for pure iron, Berry curvature is strongly enhanced at the K point, where we can see the several bands crossing at the Fermi level. So the band crossing around the Fermi level is very important for Berry curvature. And if we can calculate Berry curvature, intrinsic term of anomalous Fall conductivity can be calculated by taking the integral of Berry curvature in the Fall K-space under the Fermi level. And if we can calculate it, the sigma xy, alpha xy, the off-diagonal part of thermoelectric tensor can be calculated by this Mott equation. So here, E minus mu must be the odd function around the chemical potential, and this energy derivative of Fermi distribution function must be the even function around the chemical potential. So the energy dependence behavior of sigma xy determine the magnitude of alpha xy. Namely, if the sigma xy show that this kind of even function-like behavior, alpha xy must be small. But if the sigma xy show this kind of odd function-like behavior, we can expect the enhancement of alpha due to the contribution of intrinsic anomalous fold conductivity. So we should carefully see the energy dependence of sigma xy around the Fermi level to search the materials having the high anomalous Nernst effect. Okay, so this is very important information. So from now on, I'd like to show the experimental result in the several material. The first one is anomalous Nernst effect in the cobalt-based Heusler alloy. So as you may know, that recently, two research groups in Japan and Germany reported very large anomalous Nernst effect, the thermal power of 6 microvolt per Kelvin in the cobalt to manganese gallium full Heusler compound. Actually, this value is the highest anomalous Nernst thermal power ever reported. So here I'd like to explain why this large anomalous Nernst appear in this Heusler compound. So in order to explain, we have to see the energy band, so electronic band dispersion around the Fermi level. So here I show the electronic band dispersion on the kz equal 0 plane and kz equal pi over 2 pi over kz equals 0 plane, and this red and the blue dotted line correspond to the energy band of majority and minority spin electron. And we also calculated the Berry curvature in this kz equal 0 plane. And for this calculation, we set the magnetization direction to the x direction. And as you can see, there are several band crossing points near Fermi level in this cobalt to manganese gallium, as indicated by A, B, C, D. And when we give the spin orbit interaction for this calculation, you may see the opening of a gap at each band crossing point on the kz equal 0 plane. So this gap opening appear due to the breaking of time reversal symmetry on this plane. And if you see the calculation of Berry curvature at this energy level, 0.05 eV, as you can see, large Berry curvature appeared in between the K point and X point. So this point corresponds to the gap point indicated by A. And if you see the Berry curvature at minus 0.08 eV, as you can see, strong Berry curvature appear in between gamma and W point. So this point is corresponding to the this D. So this opening gap is the origin of large Berry curvature near Fermi level in this material. And the most important point is in this material, because of the many band crossing points near Fermi level, this material has the large intrinsic anomalous hole conductivity at Fermi level. But as you can see, when the energy level become higher or lower, this sigma xy drastically reduced. So therefore, if we calculated the alpha xy based on this sigma xy, we can clearly see the large enhancement of positive and negative alpha xy around the Fermi level. Actually, so this large alpha xy is the origin of a large anomalous Nernst effect in this material. So this kind of explanation was also done in these previous two studies. So these two studies pointed out that this formation of wide point near Fermi level is the reason for the large sigma xy and alpha xy near Fermi level. And okay, so this kind of theoretical prediction give us the motivation to work on the several things. So because this alpha XY must drastically change around the Fermi level, so it is very interesting to study how the position of the Fermi level change the magnitude and sign of alpha XY and sum of power of anomalous Nernst effect. So it is very interesting to tune the position of the Fermi level. And another interesting point is how atomic ordering in Heusler compound change the anomalous Nernst effect. So basically, this cobalt manganese gallium has this kind of L21 ordered structure. But once manganese and gallium disordered and form this B2 disordered structure, this kind of smearing of band happens. So the Berry curvature must change due to the B2 type disordering. So it is interesting to study how B2 disordering affects the anomalous Nernst effect. So in our recent in our study, we fabricated the cobalt manganese gallium germanium thin film using the co-deposition technique with cobalt manganese gallium and cobalt manganese germanium target. So as you can see in this theoretical calculation of density of state for pure CM germanium and CM gallium, so these two materials have nearly identical density of state near Fermi level, but Fermi level position is shifted by the change of total valence electron number. So from this calculation, we can expect it that the Fermi level position can be tuned by changing the composition ratio of gallium and germanium. And in our study, in order to change the degree of atomic ordering, we prepared two series of thin film. One were annealed at 400 degrees C, relatively low temperature. The other were annealed at 650 degrees C to obtain a higher atomic ordering. And in our study, we measured the anomalous Nernst effect by flowing the heat current in plane direction in this film. And we measured the temperature gradient by using the infrared camera strictly. So here you can see the Xrd patterns for this CM gallium germanium film having the different gallium and germanium composition ratio. So left side is Xrd patterns of the samples annealed at 650 degrees C, and right side is the samples annealed at 450 degrees C. So when the annealing temperature is 450 degrees C, we could not see the clear 111 super lattice peak arising from the L21 ordered structure. But we can clearly see the 002 peak arising from B2 structure. So we can conclude that these films have the B2 disordered structure, not L21 ordered structure. But as you can see on the left side, when we increase the annealing temperature at 650 degrees C, we can clearly see the L21 ordered 111 super lattice peak. So as I summarized in this figure, at 450 degrees C, we could not see the L21 ordering in full gallium germanium composition ratio. But when we increase the annealing temperature at up to 650 degrees C, we can obtain the higher L21 ordered state in every sample. Okay, here I show the gallium germanium composition dependence of thermal power of anomalous Nernst effect. As you can see, interestingly, the thermal power of anomalous Nernst effect drastically changed from B2 disordered structure to L21 ordered structure. And in this experiment, we observed the highest thermal power NE of 6 to 7 microvolt per Kelvin. And after measuring the all parameters such as Seebeck coefficient, anomalous Fall conductivity, and resistivity, finally we can evaluate the gallium germanium composition dependence of alpha XY. So as you can see, we can clearly see the drastic enhancement of alpha XY from B2 disordered CMGG film to L21 ordered CMGG film. So this result clearly suggested that the high alpha XY, for obtaining the high alpha XY, it is necessary to realize the high degree of L21 ordering. And if we compare this tendency of experimental tendency of alpha XY with the theoretical alpha energy dependence of alpha XY, we can see the qualitative agreement between the experimental alpha XY and the theoretical alpha XY. However, if our pure cobalt-2 manganese gallium has the same position of film level with the theoretical cobalt-2 manganese gallium, actually alpha XY must be very, very small. But as you can see, we observed the relatively large alpha XY even in the pure cobalt-2 manganese gallium. We speculated that this discrepancy is due to the fermi-level-based shifting due to the off-stoichiometry of our cobalt-2 manganese gallium thin film. But anyway, we clearly see the reduction of alpha XY with increasing the germanium composition as this theory predicted. So this kind of experiment and theoretical work tells us that atomic ordering and film level tuning are very important to realize the large anomalous Nernst effect in cobalt-based Heusler compound. Okay, here I showed several other our study on the anomalous Nernst effect in Heusler compound. So we also studied anomalous Nernst effect in the cobalt-2 manganese aluminum silicon thin film and observed the high anomalous Nernst effect 5.7 microvolt. And as well as the cobalt-2 manganese gallium germanium, we confirmed the importance of Fermi level tuning and atomic order in this material. And we also fabricated the cobalt-2 manganese gallium having the different composition ratio, and you clearly see the large variation of alpha XY as a function of the total valence electron number. So in this study, we check the electronic band dispersion near film level using the spin and angular resolved photoemission spectroscopy, and successfully detect the existence of wild cone just below the film level in this material. Okay, so this is a recent result of anomalous Nernst effect in cobalt-based Heusler. So as a final part of my talk, I'd like to show you the anomalous Nernst effect in the iron-based binary alloys. Okay, as you can imagine that if we can realize large anomalous Nernst effect in iron-based material, it is very promising for practical application because iron is a very abundant element in the world. However, if we measure the anomalous Nernst effect in pure iron, unfortunately, obtainable thermal power of ANE is very, very small, just 0.1 microvolt per Kelvin, and alpha XY is just 0.1 ampere per meter Kelvin. So this result can be expressed by the intrinsic anomalous fold conductivity. As you can see, in the pure iron, sigma XY show the even function-like behavior around the Fermi level. So the very small alpha XY is actually the very reasonable. So we considered whether or not we can enhance the anomalous Nernst output in pure iron by adding the other elements. So in our recent study, we try to substitute the so iron with gallium. So we made the iron gallium epitaxial thin film using the co-deposition technique with iron target and iron gallium target. So here you can see the Xrd patterns for iron gallium thin film with different gallium concentration. As you can see, we observed only 002 BCC-like BCC iron peak from x equals 0 to x equals 0.32. So this result suggests gallium atoms are randomly occupied in the iron site and randomly disordered BCC iron gallium formed in these thin films. As you can see in this EDS mapping analysis for one iron gallium thin film, we can observe the almost homogeneous distribution of gallium in our film. Okay, so we measure the anomalous Nernst effect in this iron gallium thin film. So as you can see, we successfully observed a large enhancement of anomalous Nernst effect by adding the gallium. So with increasing the gallium concentration, anomalous Nernst sum power is increased, and finally, the highest anomalous Nernst sum power of 2.4 microvolt per Kelvin was observed in this composition ratio. And after measuring other parameters systematically, we observed very interesting behavior in alpha XY. As you can see, alpha X gallium composition dependence alpha XY showed a very strange two peak like this. So why these two peaks appeared? So we performed the first principle calculation of density of state for BCC randomly disordered iron gallium. As a result, we found that by adding the gallium, the Fermi level slightly shift by the charge transfer from gallium sp density of state to the d state of iron. So this Fermi level shift gives us one speculation based on this theoretical calculation of sigma xy. As you can see, if the Fermi level of pure iron shift towards higher energy by gallium substitution, as you can see, there are two energetical levels showing the large slope of sigma xy. So if the Fermi level passing through these points, we should see the two peaks of alpha xy. So we believe that these two peaks arises from the Fermi level tuning by adding the gallium in pure iron. So we concluded that this kind of large anomalous Nernst effect was observed due to the intrinsic anomalous Hall conductivity of pure iron. Okay, so this is a result we reported in last year, but as you may know, recently very impressive data was published in Nature. This is a paper from a Japanese group, Professor Nakatsuji's group. So they found a very large anomalous Nernst effect of 4 microvolt per Kelvin in DO3 ordered iron 3 gallium. So they explained the origin of this anomalous Nernst effect is due to the large Berry curvature arising from the nodal wave around the Fermi level. So this is very impressive paper, but what we want to emphasize is the formation of DO3 phase need a high temperature annealing over 500 degrees C. But our disordered iron gallium film can be made by just room temperature deposition, which is more suitable for practical application. So to prove it, we have fabricated the anomalous Nernst effect-based heat flux sensor using the iron gallium disordered film. So because we don't need to do any thermal treatment of this iron gallium, we can deposit this film not only on the solid MgO substrate, but also the very flexible for example, polyethylene naphthalate film or polyimide film, which has the very low thermal endurance. So we deposit the film on this kind of substrate, and we pattern the ferromagnetic wire using the photolithography technique. And finally, we connected this wire using the gold. So we made this kind of heat flux sensor using the anomalous Nernst effect. And we also made a measurement setup to evaluate the sensitivity of this prototype of heat flux sensor. So in this setup, we put the ceramic heater around here, and we stack the commercially available Zeebeck-based heat flux sensor and the prototype of ANE-based heat flux sensor in between this copper heat bus and the ceramic heater. Therefore, heat flux pass through both this Zeebeck heat flux sensor and anomalous Nernst heat flux sensor. Therefore, by measuring the both heat flux and the Nernst voltage, we can evaluate the sensitivity of the prototype of ANE heat flux sensor. Okay, so we measure the magnetic field dependence of output voltage of this prototype of heat flux sensor. This is a result of the heat flux sensor made on the MgO substrate. The width of iron gallium is 50 micrometer in this device. So as you can see, the output voltage of Nernst effect increase with increasing the output voltage to heater. And here you can see the heat flux dependence of anomalous Nernst effect measured with and without external magnetic field. As you can see, in both cases, we can clearly see the linear dependence of anomalous Nernst voltage as a function of heat flux. So this result clearly indicates the anomalous Nernst effect can be used as the heat flux sensor even without the external magnetic field. And this is the result on the solid MgO substrate, a device grown on the solid MgO substrate. But because iron gallium can be grown on the very flexible sheet, we also fabricate the prototype of heat flux sensor on PEN substrate sheet. So this is a very flexible sheet, and we pattern the iron gallium wire on this sheet. And as you can see, even on this flexible sheet, we can clearly see the linear dependence of anomalous Nernst voltage as a function of heat flux. So this is a successful demonstration of heat flux sensing using the anomalous Nernst effect-based flexible heat flux sensor. Although the observed sensitivity is still not so large because the width of iron gallium wire is very large in this prototype of the device, but there is still large room to improve the sensitivity of this heat flux sensor by reducing the width of iron ferromagnetic wire. And of course, if we can find a new material showing the higher anomalous Nernst effect, we can realize much higher sensitivity in this heat flux sensor. Okay, so thank you for listening. So here you can see the summary of my talk, webinar talk today. So today I introduced the several promising applications using the anomalous Nernst effect. So energy harvesting technology and heat flux sensor. However, as I mentioned, so much larger thermal power anomalous Nernst effect, over 10 microvolt per Kelvin is required to realize this kind of application. And I also introduced several results of anomalous Nernst effect in several materials. So yeah, here you can see the summary of reported sum of power of anomalous Nernst effect. Actually, no material show the no sum of power over 10 microvolt per Kelvin so far. So the last message in this webinar presentation is, so further exploration of new material is required for practical application using this anomalous Nernst effect. So if you are interested in this topic and if you have interesting or promising material, magnetic material, so any bulk or thin films are okay. So we have a capability to measure the various thermoelectric and electric properties. So I'd like to have a collaboration with you to accelerate this work to reach the practical application as early as possible. So thank you for listening.
Okay, thank you so much for this very nice presentation. I clap on behalf of everybody. We have time for questions.
Can I ask a question?
Anyone wants to?
Yeah.
Hello.
Yes,
Yes.
please.
I like to get to the real physical meaning of this alpha XY, the thermoelectric conductivity.
Mm-hmm.
I have the
Yes.
difficulty in understanding that.
So, okay. Yeah, so I can say that the second term is very simple. So when we give the temperature gradient, so Z effect to give a exciter carrier transfer, and the anomalous Hall effect give a transverse electric field from Zedek effect. And this alpha XY can be considered as a kind of direct conversion from the temperature gradient to the transverse electric field. So, yeah.
But there are some recent papers which claim that anomalous, there are materials showing not so high anomalous Hall effect can show Nernst effect. Is this formula still valid?
Yes, that is correct, because you know, if this sigma xy is 0 at the level, but if the slope of this sigma xy is large, sigma xy is 0, but alpha xy can be large. So even the material having the low anomalous Hall effect can show the large anomalous Nernst effect from the large contribution of alpha xy, I think.
Okay, I follow. Thanks very much.
Yeah,
thanks. So we are doing.
I think so. Mahendran, you have more questions? Please go ahead.
Just one comment, Professor Sakuraba. Well, we are also working on Nernst effect, of course, with bulk materials, bulk oxides. Certainly, I'm interested to collaborate with you on some of the oxides we have made to compare the result as well as to get something new. Probably I will write to you. I'm from National University of Singapore.
Okay, I'm very happy to contact.
Okay, I'll write to you. Thank you very much.
Yeah, thank you.
Okay, the next question is by Souvik Chatterjee. Souvik, please unmute and say.
Sure. Hi, am I audible? Can you hear me?
Yes.
Okay, yeah, great talk. So I have a couple of questions, if I'm allowed. So first is quickly about you showed that ARCUS data on your cobalt, manganese, gallium, I guess. So where you said that there is evidence for wild point. So I was wondering, did you see any Fermi arc states in these materials? You know, like if you have wild points, you should see Fermi arcs on the surface.
Okay, So
it was also not very clear where exactly the wild point is. Maybe the data is, yeah, it was not very obvious.
actually, we cannot conclude, but as you can see, there is several state near Fermi level connecting to this wild point. Can you see?
But you see a small gap there, seems like, in the calculation.
Yes. So yeah, so in this paper, we could not conclude we observe the Fermi arc in this RPS measurement.
Yeah, okay. Because I mean, if you have a gap, then it's not a while, right? While you should have a protected crossing.
Yes. So yeah,
okay.
here we should have the gap. Of course, because of the resolution, we could not see the clear gap, but there must be gap.
No, but if there is a gap, then it's not a wild point, right? Wild point is a symmetry protected crossing, so there should not be a gap, I think.
Yes.
But anyway, okay, great. So another thing I was curious, you mentioned about the calculation of alpha xy, and I was wondering, and you were for your when you're comparing with your data that because you were wondering because of the L21 to B2 ordering, there might be a shift in the Fermi level. I was wondering if could you also calculate for the B2 ordering and how much lower the alpha xy will go, because you clearly have B2 ordering in your term.
Yes.
So how much does the alpha xy coefficient actually changes? So in that sense, if someone can really grow the true L21 material, how much improvement one can get? So following that direction, how much improvement in the Nernst coefficient can one expect?
Yeah. So actually, we calculated in the CMG. So sorry, today I don't have the view graph, but for example, in this paper, we show the sigma xy for L21 and B2 disordered case. And yeah, as you can, so in this paper, we show the value of alpha xy at around the Fermi level. So as you can see, yeah, alpha xy largely reduced by B2 disordering. So yeah, we saw this kind of data.
I see. And if I may, there's another quick question I had is that, so by looking to, could you get us some number, like how much was the shift in the Fermi level from the DFT, like looking at the carrier concentrations or something like that? Like what is the, because of these defects, how much is the shift in the intrinsic doping, or how much is the shift in the Fermi level due to intrinsic doping in your film?
You were asking about the Fermi level shifting. This
yeah, like so. I mean, your Fermi level is not exactly where you would expect from like a DFT calculation or from an ideal crystal structure, right?
Yes,
so I was wondering if you had some numbers, like how much you think there is a shift.
For example, in this paper, we clearly see the, for example, wild cone around here, and actually this wild cone must be correspond to the, this point C. So we, from this RPS measurement, we confirmed around 70 millivolt Fermi level shifting towards a higher level due to the off-stoichiometric compression. Yeah.
But does that match with your like transport, the carrier concentration? Is there anything that can be said from the transport measurements? If you try to make a comparison, or you probably didn't do or something. You know what I'm saying? Like you can get the carrier concentration where you fix the Fermi level in your DFT. You can get the carrier concentration out, and measuring the film if that something can be said about from that, because from RPS sometimes you also have these surface states, and though it's a metal, so there should not be any much difference from the surface Fermi level to the bulk. But if you can get something from transport, it'd be more, I think, more, I don't know, believable, I guess.
Yeah. So what Yeah, we have not performed the DFT calculation for this kind of off-stoichiometric situation. So
Okay.
we can, yeah. But what we can say is this enlargement alpha xy is due to the Fermi level shifting towards the
Okay.
higher level.
Okay.
Yeah.
Thanks.
Thank you, Soubik. Manoj Talluri, you please go ahead with your question. Maybe I will read his question. Okay. How do you ensure uniform composition throughout the structure, iron gallium or iron aluminum, from co-deposition? How do you actually make sure that the stoichiometry is?
So you mean how I could make sure the composition?
I think he meant by that, yeah.
Yes. So of course we check the deposition rate of, so for example, iron and iron gallium target, and control the power for each target and design the composition ratio. But of course, sometimes the deviation of designed composition and actual composition happens. So we check the composition by XRF for each film.
Okay, thank you. There is a question from Abhirup De.
Yes, nice talk, and thanks for this talk. I just want to know in the total expression for the Nernst singular two term, like alpha xy, this transverse Peltier term, and another one, the direct Seebeck term. So I was wondering to know the role of Berry curvature is, as far I know, it's like decibation less, so that it independent over the sigma xx. How do you explain such scenario in this formula?
So sorry, could you repeat the question?
Okay, like the role of Berry curvature
yes.
is basically dissipation less. I mean,
Yes.
it is independent over the resistivity of that part. But here in the second term is always independent over it. So how do you explain such scenario in this formula? The second term is kind of always there. I mean,
yeah, this is kind of, how to say? Yeah, of course, in this equation, we should consider the various contribution of anomalous Hall effects. So not only intrinsic contribution, but also I think the extrinsic contribution must be taken into account for this equation. So sorry,
I mean, in other way, I can ask, like in the main experiment you reported to confirm that the main role of Berry curvature is coming from alpha xy term. Okay, and instead of that, one can directly plot the anomalous Nernst signal against the Seebeck coefficient. If it is independent over there, then the Berry role is clarified.
Okay, so yeah, let's have a discussion later directly.
Yeah. Sure. I'll write to you.
Yeah, it would be actually nice. Himanshu Sharma has a question. Please go ahead.
Thank you, Sakuraba. It's a very nice talk, and I really see the discovery of that ANT by your research group is really a motivation for this such kind of anomalous Nernst effect devices. So my question is about the section of this heat flux sensor. You have created ANE-based heat flux sensor. Now, for this application point of view, we need magnetic field in order to use this such kind of like sensor. And one other option is to use the remnant magnetization to hold the anomalous Nernst value, Seebeck Nernst transverse Nernst value. So just I want your quick comment about it. Like if we use the remnant magnetization value, will the sensitivity effect of this Nernst effect, like it will become more sensitive to the application point of view, because we need to use the magnetic shielding and other things to protect from the other magnetic field around the electronics or some other things. Do you have any comment about this point?
Yeah, so you're right. So for the application, we have to, if we use the magnetically soft material for this application, we have to protect this sensor from external magnetic field. So I think that it is the best way is to use the kind of the hard magnetic material for this application. So material having the large coercivity and perfect remanence magnetization. So the material having the high uniaxial magnetic anisotropy is the very good choice for this application.
Okay. Thank you, sir.
Yeah, thank you. Actually, I have one quick question, Sakuraba-san.
Hi.
What about the CFMS Heusler alloy? How are they useful for this kind of experiment?
Actually, if we look at the calculation of sigma xy in cobalt to manganese silicon and cobalt to iron silicon, theoretically, large anomalous Nernst sigma xy has not been predicted in CMS and CFS. So in the CFMS, I think we cannot get the large anomalous fold conductivity in the CFMS. So I think we cannot expect a large anomalous Nernst effect in CFMS. But the CMA, cobalt to manganese aluminum, has very nice, has a wide point near Fermi level. So as I demonstrated in recent publication, so CMA, cobalt manganese aluminum, has a very nice, very high anomalous fold conductivity in L2 structure.
Okay. Yeah, thank you so much. Okay, I think there are no more questions. So it was very nice interactive session, and thank you so much for showing us these new directions of spintronics and really interesting results on anomalous Nernst effect. Thank you so much again from myself and my colleague Rajbhushan. And thank you all for your kind time to join this webinar. So we will meet next week. I think Professor Pinamanian from Singapore is going to give a lecture on neuromorphic computing, something like that. So until then, we see, and please stay safe and stay healthy. Thank you very much, and good night. Bye-bye.
Thank you.